centuries, Canon has been guided by working for the common good.
Good morning, everyone. Don't know whether you had an advert going on there or not. I certainly did. We've got trying to do different things here and a few technical issues. Anyway, good to see you all this morning. Lovely sunny morning. And well, it certainly is here in sunny Watford. I hope it is where you are. Right, okay, so let's just see, who have we got on? All right, we've got quite a few of the usual regulars on. Good to see you, and I can see there's a few new ones on. So, what do we do? If you're new to this, I'll be giving you some questions to try, quick-fire questions at times. There'll be a challenge question at the end, and hopefully you'll all take part. My name's Stuart, by the way. I'm the guy who does all the videos that you see on ExamSolutions.net if you haven't been there before. And I have Michael online doing the live chat as usual, helping out, so he'll answer any of your questions. Okay, so what are we going to be doing today? Oh, one thing. I did say on the last workout, if you were with us, I set you a challenge problem there. And it was great to see the response I got back, people writing their answers in the description below the last video workout. And the first person with the correct solution was Isabel. Okay, so well done, Isabel. And a few of you also took part and got the right answer. If you go back to that video, the last workout, you will see there's a link now to the work solution. So, good that you did that. Okay, so same thing's going to happen today. As I say, we'll have a challenge question. You'll see if you can put your solutions in the comments below the video when the preview finishes, and be first to see who gets the solution. Okay, so what are we on today? We're on optimizing. We're going to be looking at maximum and minimum areas and volumes, and I'm sure some of you could well have done this before. If not, okay, hopefully you'll gain something from this, okay, as well. Right, okay, so we're going to start off. Okay, let's just take this next slide. Okay, now I did put out on Facebook and in Twitter, okay, that it'd be great if some of you guys could just take an A4 sheet of paper. Typical A4 sheet of paper measures 210 millimeters by 297 millimeters, and cut out equal size squares, okay, any length you like. I called that length in general X. Any length from each of the four corners of your A4 sheet, and then to fold up these sides and make a box, okay? And what I wanted you to do, okay, was to measure the value of X that you had, and then work out, or just not work out, let's say just measure your length and your width and your height X and work out the volume. And on the side of the box, write down what the length was and what the width was, what the volume was, I should say, and what the height of your box was, X. And some of you guys posted in your creations, and I'd love to see what you did. It was good to see. Let's just put up these values just to say you had to work out the width, length, and the height and get the volume. Okay, so the volume, as you know, is the height times the width times the length in any order there. Okay, so let's have a look at some of these creations. I had a box here from Din. Din, I can see you're online at the moment. Well done for sending your box in. You had a height X of 7 centimeters. I hope you guys can see that out there. And when you folded it all up, you got a volume of 769.3 centimeter cubes. And then we had David. David came in with a box. Okay, now his box was a lot thinner. Okay, you can see here in the width. All right. The width was 1 centimeter. He cut out squares of side 10 centimeters and the volume turned out to be 94 centimeter cubes. So you can see a different type of box here. Okay, still all cut out from the A4 sheet. And then Susan made a box. Okay, Susan happens to be my wife, and she made this box for us. Okay, you'll see here it's totally different in size to these ones here. She cut out a square from the ends of 5 centimeters, so that was that height there, and the volume turned out to be 1083.5 centimeter cubes. So what I did was to plot these values that you guys had on a graph. Okay, I've got the volume V here. Okay, we're measuring in centimeters. Okay, so our X is measured in centimeters, the volume would be measured in centimeter cubes, and you can see I've plotted David's point here at X equals 10 and the volume turned out to be 94 centimeter cubes. So trust me, that is at 94. Okay, because it's going up in 100 intervals. Okay, Din here with his measurement, X is 7, the volume was 769.3, and Susan with X is 5 and the volume 1083.5. Okay, so what I'd like you to do, okay, or where am I going with this? Well, basically, when we're looking at this, you can see that given this one sheet of paper, we can make different boxes. These are just a sample, okay, of the boxes we can make. But the question is, what is the box that gives us the biggest volume? At the moment, it's Susan's box, okay? But is there a particular size of square that you have to cut out here that gives us the biggest volume? Okay, and that's what we're trying to do in this particular presentation. And to do this, what I would like to do is, first of all, ask you guys to give me, okay, what the width would be, okay, in terms of X. Okay, look at this sheet of paper, tell us what the width would be in terms of X. Just enter it in there. Okay, what would that width be? Quite often you're asked these kind of questions, or you need to be able to answer them when you're doing these in exam situations. What would this width be in terms of X? Anybody? Okay, now there's going to be a slight delay here, about 30 seconds if you've not been on these live streams before I actually see what you type in. So do bear with us, okay? Just want that width there in terms of X. Okay, nobody? Ah, right, David coming in with 21 minus 2x. Anybody else agree with that? Din, 210 minus 2x. Remember, these measurements, by the way, are in centimeters. Okay, I needed to mention that to you. Okay, so I do understand why you're saying 210 minus 2x. So well done for having a go at that. But David is right, because it's in centimeters. 21 minus 2x. Okay, That's good. Okay, so that's the width. Let's just put that width on there. Okay, 21 minus 2x. So what would the length be? Okay, we can see by the way the width here, okay, is going to be the 21 centimeters across here minus the 2 distances here, which are going to be x. Okay, so have a go at giving me quickly the length. All right, and I see Kaz, sorry I'm not up to doing calculations at the moment, poorly in bed. Okay, well thanks for coming along, Kaz, hope you get better soon. Okay, and good luck to you. All right, wish you the best. Okay, Isabel, 29.7 minus 2x. Well done, coming in first there. Din as well, a lot of you coming in there. Yes, very straightforward. The length here is going to be clearly the 297 millimeters, which is 29.7 centimeters. Take away those 2 sections there, the 2x. So 29.7 minus 2x. So what I'd like you to do now is, well, what we're going to do, let me just remove these pictures. Sorry, we'll just bear with me one moment while I remove the pictures. Give us a little bit more space, okay? And we've got the length back there, okay? And we need to remove Susan's box. Okay, there we go. Okay, so we've got a bit of space on the screen now. So what we're going to do is create the equation for the volume, okay? So clearly I'm going to need to multiply all of these values together. So if we do that, okay, we're going to get this expression down here, okay? X times all of 21 minus 2x times 29.7 minus 2x, okay? Now I'm not going to ask you to expand that, okay? I'm sure you guys can already do that. I've just expanded the last 2 brackets, okay? And we've got this result here, and then I'm just going to multiply through by the x. Okay, so there we go. 623.7x minus 101.4 x squared plus 4x cubed, just in case you can't see that. Okay, so what does this allow me to do? Okay, it allows me to graph this curve. Okay, now if I graph the volume against the varying size x that we cut the squares out of, okay, then the graph will look like this. It's a cubic graph, so we would expect this kind of shape, okay? It comes up here, down here, into the negative part there, below the x-axis, and up through here. Now, from the practical point of view, obviously x has to be a positive value, and it means that we're looking for a value of x in this region here, okay? You can see the graph crosses the x-axis when v equals 0, and when it's factorized you can see that that will be when x is equal to 21 divided by 2, 10.5. That's that point there, okay? And this point here will be 29.7 divided by 2 when each of these factors are equal to 0. Okay, so we're only interested in this section here, and the greatest volume you can see occurs for some value of x. It looks to be around about 4 here, but is it 4? And it gives us this greatest volume, and that's what we're trying to find now, how we get the value of x that gives us this value. We can read off the graph, yes, and it looks to be about 4, but as I say, is it exactly 4? Well, I'm sure some of you guys most probably know how we do this, but for those that don't, just going to show you, okay, and then we'll get you into a problem very shortly, okay? Up here and down here are called stationary points. I've got them in blue here, okay? They're called stationary points because at those points the gradient given by this tangent here, the gradient is 0, it's horizontal, okay? And we should know that to get gradient you need to differentiate, and when you differentiate at a stationary point, these points here given in blue, dv by dx would be equal to 0. The gradient would be 0. So if we're to find out what this value of x is, that gives us this biggest volume, we need to differentiate this equation. Okay, so what I'm going to ask you to do is, could you differentiate this equation for me? Okay, could you differentiate that and just give me your answer? Okay, just type that answer in if you can. Okay, let's see who can differentiate that first. Give us dv by dx. Okay, so just asking you if you've just joined us to differentiate this equation. We're looking at optimization, optimizing areas and volumes. Ella's got an answer. Okay, good. Okay. Right, okay, good to see that you've done this, both Ella and David. Okay, well done, because that is the answer. You should be familiar with basic differentiation. Let's put the answer up here. Okay, good. Erica coming in, that's fine. Okay. Right, and Din as well, following in, okay, with answers. Good. Obviously, it doesn't matter the order you put this in. Now, if we're to look for that maximum volume, we know that dvx must equal, dv by dx must equal 0. So, we're going to set up that equation equal to 0, okay? Just put it in there. There we go. And I want you to be able to tell me what the value of x is, okay? So some of you guys might have worked on ahead of me already on this, anticipating what the question was if you've covered it. We're looking to solve this equation. How would I go about solving that? It's got some complicated numbers in, so it's not going to factorize. So we've got to use, obviously, the quadratic formula. Okay, so Ella coming in with an answer. Okay, let's give our answers to 1 decimal place. Okay, so I know Ella and Isabel have got answers at 4.04. Okay, that was good. Okay, if we go for 1 decimal place though, what's it going to be? Okay, we've got 2 values of x coming in from T2. Interesting, it's good to see that. But good, it is in fact 4.0, okay, to 1 decimal place. So it's not quite 4, it's 4 and a little bit more, okay, and that's why that 0 is important behind there. It's telling us that there were other digits there. Good, so you might have done it via your calculators if you've got the quadratic formula already programmed in, okay, but here it is here. X equals, okay, the usual formula. Remember, we have a x squared plus bx plus c equals 0. A is 12, b is minus 202.8, and c would be 623.7. So using the quadratic formula, x equals minus b plus or minus the square root of b squared minus 4 times a times c all over 2a. You're going to get that sum, and indeed it works out to give us these answers, okay? Now, we do get 2 values of x, 12.857, which I did notice someone put down. I think it was T2, yes, 12.9 to 1 decimal place. Notice how that's giving us the x value for this stationary point here. The one we're interested in is this one here, x equals 4.042 and so on, okay? And when rounded to 1 decimal place, it is going to be 4.0. Okay, so just a little bit more than 4. Now you'll notice I've given you the corresponding volume. And you can get that. I won't ask you to do it, but you just substitute your value of x into your equation here for v, and out will pop the corresponding volume. 1128.49 and so on. So if you were to put those answers in, we've got the maximum volume is 1128.5 centimetre cubes when x is 4.0 centimetres. Both of these given to 1 decimal place, and you can see that from the graph. Okay, so so often I see people doing these kind of max and min questions, and I wanted to do this problem in relation to a practical example and use a graph just to show you what is actually happening, okay? Just in case you had missed the point. Right, okay. Well, the next thing I just want to do is just very quickly show you that if you didn't have that graph around, you're often asked to show that the value of x that you have worked out gives us a maximum or a minimum. Now, just want to give you some notes here very quickly, just in case you're unsure of this. One way, a good way of generally finding if a point on a curve is a maximum or minimum, it's not the only way, but this is sufficient for what we're doing here, is to look at what we call the rate of change of gradient. The rate of change is given by d by dx, and the gradient function is dv by dx. And when you've got a curve going like this, okay, oh, by the way, this gives us d squared v, or d2v, over dx squared, okay? So it's a rate of change of gradient. So when you've got a maximum on a curve, notice how the gradient is positive, then 0, then negative. And what's happening is that if you think like a gradient, say, was +2 here, 0 here, and -2 down here, if it were like a thermometer going from +2 to 0 to -2, we would say that it was decreasing. So what we've got here is the gradient is decreasing as we go from left to right. So we would expect that rate of change of gradient to be a negative value. And we have a similar argument when we have a minimum on a curve, okay? We're going from a negative gradient, say -2, to a flat gradient, 0, up to a positive gradient. Let's say that's +2. So if you're going -2, 0, +2, if it were like a temperature, you'd say the temperature is increasing. Well, the rate of change of the gradient is increasing. That's given by d2v by dx squared in this case, okay? It's positive. So, if we didn't have that information, that graph in front of us, okay, then what I want to do is we'll just recap. We found that formula for the volume, okay, to be this formula. We differentiated it, okay. Now, what I'd like you to do is just tell me what d2v by dx squared would be, okay. Just write down what d2v by dx squared would be. Okay, -202.8 plus 24x. That is correct. Okay, both David and did Ella get that one? I think you might have missed out the negative, Ella. Okay. But yes, when you differentiate that again, do that double differentiation, that's what you get, -202.8 plus 24x. And what we need to do is test that point that we found, okay, whether it gives us a maximum or minimum. Remember, let's imagine that the graph wasn't in front of us, okay, so we have no idea. So what we would need to do is think about that value of x that we're testing. It was 4.042 and so on. Substitute it into here, see what we get, okay? Well, if you do that, okay, sub it in, you'll find that you get negative 105.792 and so on, which is a negative number. It's less than 0, okay? So if it's less than 0, we know we've got a maximum, okay, as we go round here. But as I say, remember, think that the graph wasn't here, okay? This is how we would handle it if the graph weren't there. Okay, so I hope that's clear for all you guys out there. Right, okay, so in summary, then when x is 4.0 centimeters, the volume is a maximum. Right, okay, well, let's just go to another question, okay? Now, in this question, this is the last question before I give you the challenge, all right? This is, I picked this one purely because if you watch my last video, live stream, we were talking about sectors. And I think this is quite appropriate. It's a nice follow-on from that, okay? What we've got here is a farmer then has 60 meters of fencing and decides to enclose an area in a field in the shape of a sector, okay? My question to you is, what is the radius and the angle of the sector needed to create the largest area? Now, if you are happy with this, I'm sure you might like to just go on and work it out as I chat through, okay? But I'm just going to take you guys through this fairly slowly, get you to interact, okay? Now, if we've got 60 meters of fencing, there are different types of sectors I'm sure that you could do, from thin ones to shapes like this to ones like this, all having a perimeter of 60 meters, okay? The question is, which one of these, if it is one of these, is going to give us the biggest area? And if so, our job is to find out what the radius would be and the angle of the sector. That's the angle in here, okay? There, or even round here, okay? Wonder what it would be. So how do we do questions like this? Well, let's just take our sector in general. Let's say something like this, okay? So I've got the radius r, I've put in the length of the arc, and I've put the angle theta subtended between the two radii, okay? Now, what we need to do is eventually try and get an equation for the area, which I'll call A, in terms of one letter. Let's say the radius, okay? If we could do that, then we'll be able to differentiate it and find out what R would have to be to give us that biggest area. So we're trying to get an equation for the area in one variable. And at the moment we got three variables here, R, theta and L. Okay? So what we need to do, okay, what we're going to do is first of all find out what the area is in terms of R. Okay? In terms of let's go for the area in terms of R. Okay, just can you put that down for us? Okay, it'll involve theta as well. In terms of theta and R. Okay, we're going to rush on a bit here. Okay, you should be familiar with the area of a sector. We covered that in the last tutorial, or should I say live stream. Here it is, okay? Should remember that that area was a fraction, okay, of the area of the circle. That fraction being the angle theta over 2 pi radians, okay? That's the equivalent of 360 degrees. Theta compared with 2 pi of pi r squared, okay? Right, good, Erica. So what happens is the pi's cancel out and we end up with our area as being a half theta r squared, okay? So I've called that equation 1. So the next thing I want to do is figure out another equation. I want you to give me the arc length L and find theta, the angle theta, in terms of L and R. Okay, can you do that? Well, you did actually do this in the last live stream. Could you work out what the arc length L is in terms of L and R? Okay, so find theta in terms of L and R. Do you think you could do that? Going to need to build in another equation and use simultaneous equations here. Right. Okay, I'm going to push on a bit soon if we don't get any answers in. Okay, the arc length anyway, L, is going to be r theta. Okay, it's good to see that. Okay. Right, look, I'm just going to put some stuff up. Okay, the arc length, L, is r theta because it's a fraction of the circumference, as we covered before in the last live stream. The 2 pi's cancel out, okay, and that leaves us with L equaling r theta, or theta r as I've got here, and then we can rearrange this for theta. Theta is L over r. Okay, good. I can see Phet has got L over r for theta there. Brilliant. Okay, it's quite tricky this. Okay, now what I want you to do is now give us what that area is, okay, in terms of L and R. Okay, can you give us the area in terms of L and R? What's that going to be? What do you have to do between these two equations? Okay. Right. Okay, we're looking for the area now in terms of L and R. Okay, good. Good to see the answers coming in. All right. Both Ella, Natalie, and T2. Looks as if you've got the right answers. Good, because all we're going to do is substitute equation 2 into equation 1. Substitute L over R in place here, okay, which I've done here. The R's cancel and you are left with the area is half LR. So what we've now got is an equation for A, not in one variable, but in 2 variables here, okay, L and R. We still got to work towards getting A in terms of 1 variable. So what do we need to consider? Anybody out there? What do we need to consider as another equation? Where do we turn to? Okay, anybody? Where do we turn to get another equation? Good. I take it, David, when you say P, yeah, you're meaning the perimeter. Good. Okay. Right, T2, the perimeter, that's right. And Colin's telling us what that perimeter is along with Isabel. Okay, we know it's 60 meters, and that was my next question. What is L going to be in terms of the perimeter? We know the perimeter is 60. We know the distance all the way around here is 60. So 60 will equal twice the radius plus the arc length. And if we rearrange this for L now, in terms of R, we get 60 minus 2R. You could make R the subject here. It doesn't matter. But that's going to create a fraction, and I want to avoid fractions as much as possible. So what I'm doing is we've got L here. We've made L the subject. And what I'm going to do is we substitute equation 4 into 3, and we'll get an equation for A in terms of 1 variable, that variable R. So if we do that, there we go. All right. Area is a half times L, which is now 60 minus 2R times the R. And if you expand this out, you're going to get A equals 30R minus R squared. Okay. So after all of that, quite a lot of work, quite a lot of stages, we found out the area A in terms of 1 variable. So now we're in a position to find out that maximum area. To do that, you know what we've got to do? Okay, we've got to differentiate this. So that's my question to you. Differentiate this. Very easy to do. Okay, put dA by dr equal to 0 and tell me what that radius is going to be. Okay, I will bring up the solution very shortly, but you should be on your way now. Okay, David coming in with r is 15. I suspect you might have been working ahead. Okay, check your units, by the way. Okay, we're looking for the right answer. We're coming in now. Yes, guys, r is 15. Well done. Okay, let's quickly run through it. You've got to differentiate it. If you differentiate in the usual way, something like this, then it's going to be 30 minus 2r. Put that equal to 0. Okay, at that stationary point, dAr equals 0. So you have got 30 minus 2r equals 0. And if you rearrange that, 2r would equal 30. Divide both sides by 2 and r is 15. Okay. The units, by the way, are meters, not centimeters, in case you did put centimeters down. Okay, it'd be a very small fence for a farmer if it was in centimeters. Okay. So what we need now is to get that corresponding length, okay, and that angle. Right, we've got to head our way towards working out what theta would be. So we need the length here. We can get the length from 4. Just substitute 15 into here and that will give us our length. Okay, has anyone found the angle yet though? Okay, has anyone found theta yet? Good, fruit fly with 2 radians. Good, T2 with 2 radians, Natalie with 2 radians. You're all right, good. Right, so just to get that, substitute the radius is 15, okay, into equation 4. That will give you L at 30 meters. And then you can go into equation 2 with your values of L and R. And if you substitute those in, you're going to get theta equals 30 over 15 and it gives you 2 radians. Okay, well done. And you should remember what a radian was. It was approximately 57 and a little bit more degrees. So 2 radians is going to be a sector, something like this. Okay. Now, just in summary, okay, the maximum area, R is 15 meters, and the angle, okay, is 2 radians. You'll notice I purposely put a C here. We talked about that before, okay, that you can use C to describe radians. Okay, so let's just move on now, okay. I would like to leave you with this last question, okay. Now this question that's going to come up when it does, there we go. All right, follows on. Now this is quite a challenge question. This is what I'm going to leave you guys with, okay. It really, you've got to be doing A level really to be able to do this one, okay, because it's going to involve the quotient rule and also what else is it going to involve? The chain rule. Now the chain and quotient rule and the product rule I will do with you next week, okay, as tutorials. But if you happen to know how to do these, okay, then you might like to have a go at this question and put your answer in the comments box, okay. It is a bit involved, so that's why it's a challenge question. If you can't do this one, what I would suggest, if you go into the description below the video, this one, you'll see that there's a link to some exam questions on the kind of topics we've been doing in this live stream. Okay, so you might want to have further practice on that. But for this question, let me just quickly describe it to you. We've got this right circular cone. That means that the vertex here is directly over the center of the circular base here. Okay, it has a volume of 500 centimeter cubes, and Your problem is to find the height in centimetres of the cone. Okay, that's that perpendicular height straight up from the vertex here to the centre of the base. Okay, that gives a minimum curved surface area. The curved surface area is the curved surface around the cone, not the base. Okay, and I want your answer to 1 decimal place. Now, what I've drawn here is a little bit of a hint. Okay, the net of the curved surface of a cone, that's if you were to cut a circle out and take a sector out of it and join these two green bits together, you would form a cone. Okay, so that is kind of like that edge over there. Okay, you might need this, well, not might, you will need this formula. Okay, the volume of a cone is 1/3 the area of the base times the perpendicular height. Okay, in order to do this. And some other stuff. As I mentioned before, you're going to need to use the quotient rule and the chain rule. Okay, so it'd be good if you want to stretch yourself, that you have a go at that. Okay, and put your answers up. Okay, so yeah. Okay, welcome back anyway. So do check out that question by playing the video back through. Okay, afterwards. As I say, plenty in the description below with links to exam questions on this that you should be able to do for further practice. Quite a tricky topic, quite involved, but essential, okay, if you're doing AS level and A level. Okay, so anyway, I'm going to sign off here now. Okay, enjoy the rest of the day. Hope you do too. Thank you to all of you who took part. And thank you to Michael for answering your questions. Okay, so Michael will be back tomorrow. I'm having Friday off. Okay, and I'll be preparing for Monday, Wednesday and Friday of next week. Okay, so hope to see you then. Okay, bye for now. Bye.